So once again, welcome to another topic. Today we're going to be covering something referred to as waveguides. And waveguides are generally rectangular or circular in shape. And their only purpose is to convey the electromagnetic wave from one point to another. So because of that, it basically uses the principle of total internal reflection and the skin effect. With the skin effect is that at higher frequencies, the conduction is on the surface of the conductor and not actually the cross-section of the conductor. Because of that, then we are able to convey the energy from one point to another. So sometimes these are basically found in transmission equipment and particularly next to an RF power amplifier because of the easiness of conversion of the RF wave to an electromagnetic wave, and for that purpose, for us to convey it from energy from one point to another. So waveguides. They are generally rectangular. Are used to convey electromagnetic energy from one point to another. They use the principle of total internal reflection and the skin effect. So with the skin effect, the skin effect at high frequencies, the conduction is on the surface of the conductor. Then we are talking about the boundary conditions. With the boundary conditions for us to have the wave propagating inside a waveguide. So these boundary conditions is what will enable the electromagnetic wave move within the conductor from one point to another. And because of the waveguide being polarized at the edges in the vertical or horizontal axis, there must be some conditions that we need to know. So at the surface of conduction, the boundary conditions to be satisfied are 1, the electric field must be perpendicular to the surface. The electric field must be perpendicular to the surface, or else it will short circuit, or else it will short circuit the currents. This means that the tangential It means that the tangential component of the E field must be 0. This means that the tangential component of the E field must be 0, whatever referred to as must vanish or disappear. So number 2, the magnetic field must be tangential to the surface. Magnetic field must be tangential to the surface. And therefore, if the magnetic field is tangential to the normal component must be 0. And therefore, the normal component must be 0. So we are going to look again at factors on waveguide selection, factors we need to consider when choosing waveguide selection criteria. The factors considered include: number 1 is the operating frequency. When we're looking at the operating frequency, what must be the condition for us to ensure that the propagating wave is able to move from one point to another? And therefore, this operating frequency must be great enough to overcome the minimum condition. And therefore, the operating frequency must be great enough so that it's propagated. It must be great enough. It must be great enough. It must be great enough so that the energy in an electromagnetic wave is not lost. What is the factor number 2 we need to consider is attenuation at operating frequency. Attenuation at the operating frequency. This means that at any other frequency, the waveguide must not conduct. Point number 3 to consider is whatever has a physical size they should be small in size due to the fact that they are mostly mounted at greater heights and so for easy handling. And so for easy handling and mounting, the size will be key. Then number 4, we need to also see that here is the weight. Due to their construction feature, i.e., being hollow, they are light in weight. So you go to factor number 5. They should be available. They should be available at reasonable prices. So we are going to look at the definition of terms. In Waveguides. So when looking at definition of terms, we are looking at various terms that we shall be meeting in a frequent interaction with this topic, and particularly what they refer to when they are described under this topic. So the first term I'm going to refer to this as is the modes. Modes. So the modes refers to the methods in which electrical energy is able to propagate. This refers to methods through which methods in which electrical energy is able to propagate from one point to another. They include Roman 1, transverse electric, what I refer to as TE mode. In this mode, no component of electric field is in the direction of propagation. Then we go to Roman number 2 is transverse magnetic. the first TM mode. Equally, in this mode, no magnetic field is in the direction of propagation. In other words, when you look at the conditions for the TM and TE mode, we're going to realize that one thing: once the electrical field is in the direction of propagation of the TE mode, then that conduction will short circuit and we shall never have propagation from one end to another. So for us to propagate the E field in the electrical mode, it must be in the vertical and not in the opposite direction, or it must be transversing and not going in the same direction. So our term number 2 that we are going to look at, whatever is referred to as the cut-off frequency. Cut-off frequency, whatever referred to as FC. C is a subscript for cut-off. C is a subscript for cut-off frequency. So when we refer to this refers to the frequency below which no propagation is possible. This refers to frequency. The frequency below which no propagation is possible. Then we're talking about also the third term is the cut-off wavelength. What I refer to as cut-off wavelength. So a cut-off wavelength is the largest free space wavelength. It is the largest free space wavelength. The largest free space wavelength that is just unable. That is just unable. That is just unable to propagate inside a waveguide. That's just unable to propagate in a waveguide. Just unable to propagate. Just unable to propagate in a waveguide under the given conditions. Under the given conditions. We are going to have a fourth terminology as guide wavelength. Wavelength. And some books refer to this as guide wavelength. Other books will also put a subscript G. That you become aware of that. So it is the distance that the wave must propagate to experience a phase change of 2 pi radians. Phase change of 2 pi radians. And it depends on the cut-off wavelength. And it depends on the cut-off wavelength and the free space wavelength. Our term number 5 is group velocity. That's Vg. It is the velocity at which the wave must propagate in a waveguide. Our sixth term is the phase velocity. The phase velocity refers to the rate at which the electromagnetic wave, it refers to the rate at which the electromagnetic wave must propagate to experience a phase change, must propagate to experience a phase change, of the guide wavelength. So this basically whatever we shall be having in terms of terms. So basically we shall find these applications in terms of mathematical expressions in some of the examples we're going to be having in question and answers. So we're going to talk about the types of waveguides, then types of waveguides. So the first one we're going to have is the rectangular waveguide. So the rectangular waveguide will appear in this manner. This is the shape at least we expect to see in a rectangular waveguide. This is the longest side A and this is the shortest side B. So we shall be having this in terms of the rectangular waveguide, and we look at a projection, so that if you are projecting a signal, it must hit at the surface, and because of the total entire reflection, it shall be moving along that path. So we shall have such a thing. So that's an example of a rectangular waveguide. We are able to move within the rectangle and propagate towards the end. So the rectangular waveguide has got one longer side and another shorter side. So when we need to understand this, so that when any time you are being asked on anything, this should be the guidance in terms of determination of the factors that we have discussed as some of the terms that apply to waveguides. it has the dimensions. It has the dimensions A and B, A being the longest side, while B the shortest, side. So it acts as a band pass filter that attenuates. It acts as a band pass filter that highly attenuates frequencies below the cutoff and frequencies twice the cutoff. So another thing is that for TE and TM mode normally have a slightly difference. For TE mode, then Roman 1, the cutoff frequency is given by so we have this where Vc is velocity of light as normally given as 3 times 10 power 8 meters per second, and this is the cut-off wavelength. So Roman 2, the cut-off wavelength this one is given by 2 over m over a squared plus n over b squared into square root. This is a where m and n, where A and B are dimensions of the rectangular waveguide, and m and n are integers as described, are integers that are subscripts, are integers that are subscripts as described in TE mod, i.e. can have TE 1, 0. So this becomes M and this becomes M. So Roman 3 is what helps us to ask characteristic impedance ZO. So ZO is supposed to be ZFS, 1 minus lambda over lambda C squared. So when you look at that, where ZFS is the free space impedance. Free space impedance, which is normally 120 pi ohms, and ZO is the characteristic free space, the cut-off wavelength. FC is the cut-off wavelength. And lambda is supposed to be the free space wavelength. So this is supposed to be given VC over F, and cut-off is supposed to be VC over cut-off frequency. So take note of these terms here, so that in time they're placed here. So ZFS can also, ZO can also be presented by, ZO can be expressed as, ZO can also where F is the frequency of propagation. Frequency of propagation of the wave. For TM mode, then the only formula that changes is the characteristic impedance. Which then becomes ZO is supposed to be ZFS into, let's see, squared. So for TM modes, it becomes a multiplicand. For TE modes, it becomes a divisor. Basically, that's what it is, so that we are able to get just a single example before we go to the circular waveguides. So we can have an example for this case. Let's have an example so that we can be able to apply all those things we have discussed above. So a rectangular waveguide measures measures 2 by 3.5. Measures 2 centimeter by 3.5 centimeter internally. And has a 12 gigahertz signal propagating and has a 12 gigahertz signal propagating in it. For a TE 10 mode, determine Roman 1, the cut of wavelength, Roman 2, the cut of frequency, Roman 3 is the guide wavelength, Roman 4 is the group velocity, Roman 5 is characteristic impedance. We can even have the Roman 6 as maybe phase velocity. So this is an example of a question that will give us all the formulas that we applied there. But we will be given a condition that is for a TE10 mode. So in this expression, from the formulas we have had, is that for TE10 mode, then M is 1, N is 0. M is 1, then N is 0. Those are the subscripts that we described earlier in the TE mode and TM mode. Normally, these subscripts are used as numbers or integer in the applied formulas. So we're going to go through this as an example, then we shall be able to move on to the second type of waveguide. So we're going to handle our first question as this question is the cut of wavelength. So from the formulas that we have, our cut-off wavelength is supposed to be given by 2 over m by a squared plus n over b squared into square root. But for this case, we have m being equals to 1 and n being equals to 0. So logically, we are going to see that the second expression in the denominator becomes 0 because n is 0. When you have that, then it becomes this equally cut off is supposed to be 2a from the formula, given that n is 0 to a. And let us take note that a is supposed to be 2 centimeter. A is supposed to be 3.5. The longest side is A is supposed to be 3.5 centimeter, and B is supposed to be 2 centimeter. We agreed that A is the longest side and B is the shortest side. So from that, we are able to just apply this formula and proceed on. So our cut-off wavelength is supposed to be 2 times 3.5 centimeters, which becomes 7 centimeters or 0.07 meters. So that's how simple it is when applying this formula. So long as you know the parameters of the expression, it becomes very easy for us to apply that. So anytime this n is a 0, then the formula is reduced to 2a. And given that m is an integer which is 1. So anytime the integers that describe different formulas, then you must insert them using that formula. This formula only applies with the condition that n must be 0. So our Roman 2 was asking us to determine the cut-off frequency. Cut-off frequency. FC. Remember, FC is supposed to be VC over cut-off wavelength. So we remember that, then VC is 3 times 10 power 8 over cut-off wavelength. We have the cut-off wavelength as 0.07 meters. Then we divide this, we are going to get the formula 4, this becomes 4.285 times 10 raised to power 9 hertz. So we're going to go to our third term, which I'm referring to as the guide wavelength. Yes, guide wavelength. So a guide wavelength will be the free space wavelength over 1 minus a free space plane over the cut-off wavelength, and this is tidy squared. So that's the formula for a guide wavelength. Our guide wavelength, that's the formula for a guide wavelength. And we have to remember that the free space wavelength first, we have to time the free space wavelength is VC over F. And this is 3 times 10 power 8 over the frequency is 12 times 10. It was 12 gigahertz. Gigahertz is in power of power 9. When we have that, then we shall be able to proceed on as we shall have a guide level of 0.025 meters. Then we come and insert the formula in the guide wavelength. So our guide wavelength is supposed to be 0.025 meters. Then we shall have this as 1 over 0.025 over 0.07. And this becomes squared. Then insert our formula, there we shall have a guide wavelength as 0.0267 meters. So our fourth expression was to get the group velocity. The group velocity as Vg. The group velocity is, get this from the formula. That's the group velocity. And you also know that all these factors, we have them. So we shall have this factor as 3 times 10 power 8 into this is a free space wavelength 0.025 over 0.07 squared. It's a multiplicand for group velocity. Then this shall have this as, if we're going to be multiplying this, we shall have this as 2.8 times 10 power 8 meters per second. Then we shall be having, our fifth term was the characteristic impedance. ZO. So our ZO was supposed to be ZFS, which is the free space impedance. Which then becomes ZFS is 120 pi or 377 ohms. And this it gave us a result of 403.609 ohms. So we're going to go to our last part, which is the phase velocity. So our last part is the phase velocity, and the phase velocity with that abbreviation. So phase velocity is talking about Vc 1 minus lambda over lambda c squared. That's the formula. So we shall have that as 3 times 10 power 8 over 0.025 over 0.07. This is squared. When we divide that, we're going to have a formula. Our formula is 3.21 times 10 power 8, 3.21 times 10 power 8 meters per second. So this basically this is how we are going to be applying these formulas. And this is a good example of how we can use those formulas and how they're related. There's something also needs to note comparing the phase velocity and the group velocity, is that the phase velocity appears to be greater than the group velocity. And the reason is because the component 1 minus free space wavelength over cut of wavelength squared, that expression itself should give you a fraction. So long as you're dividing by the fraction and multiplying by a fraction, anytime you divide by a fraction, it becomes a greater number. So that's why we have this. That's something you need to note concerning these formulas and why we're talking about the phase velocity. So we are now going to go to what we refer to as the circular waveguide. So this one, the circular waveguide, this is our number 2. We are talking about the one was rectangular. This is number 2 circular waveguide. So this is a circular. So they'll appear in this format. So in this case, we are talking of the radius of the circle. And because the internally is hollow, the conduction is just on the surface. For circular waveguide, then the only thing that we need to change is the cut-off frequency, the cut-off wavelength. The cut-off wavelength is what determines whatever we need to change here. So for circular waveguide, the cut-off frequency, is given by 2 pi r. Where r is the radius of the waveguide, and kr is the Bessel function. Bessel function. So this is basically whatever will now come up as a new thing. So anytime we are talking about this, know that provided it's a circular waveguide, then this is what we need to know as basically the difference in terms of the applied formulas. Otherwise, the rest of the formulas remains the same. And for that case, maybe I can give you, we can have an expression of an example of how that can be applied. We can have an example of that so that we can actually look at the difference. A circular waveguide, whose internal radius is 2.5 centimeter, operates on an 8 gigahertz signal. Operates on an 8 gigahertz signal propagating in the TE mode. Taking Bessel function equivalent as 1.84, okay, as 1.84. Determine Roman 1, the cut-off wavelength, Roman 2, the cut-off of Roman 2 is the characteristic impedance. So basically, you can have those as examples. So we look at it this way. For any time you're talking about the circular waveguide, irrespective whether it is TM or TE mode, then we don't need to use the formula that we used in the rectangular form because this is circular. The basic thing we need to know is to come up with the cut-off wavelength. So our Roman 1, the cut-off wavelength is supposed to be 2 pi r over kr. So this is supposed to be 2 pi times 2.5 times 10 negative 2, because let's change that into meters, over 1.84, which is the Bessel function. And this is able to give us what I refer to 0.0853 meters. So basically, this was changed. Then we go back to the other formulas. For TE mode, then our characteristic impedance is supposed to be ZFS over 1 minus that cut-off squared. And we know this as what? We know this as our lambda is supposed to be VC over F. Then this is supposed to be 3 times 10 power 8. Our frequency of propagation was 8 times 10 power 9. When you divide this, then we're able to get as 0.0375 meters. Then we replace this in the formula, then here we shall have this as 120 pi over 1 minus 0.0375 over what we refer to as the cut-off wavelength. Cut-off wavelength is 0.0853, and this is squared. When you divide that, then we are able to get a formula as Gauss impedance as 420.90 ohms. So I think we have now learned how we can apply the circular and the rectangular waveforms. So finally, we can now have what we refer to as what are the causes of losses in waveguides and advantages of losses in waveguides. And advantages of waveguides, not causes of losses in waveguides. Attenuation in waveguides. So attenuation are the losses that occurs in waveguides, and they're mainly due to two things. Number one, losses due to absorption of energy. Absorption. Losses due to absorption of energy. On the surfaces by obstacles. We talk of the obstacles, then we can also talk of the things we taught as discontinuity. Discontinuity of the surface. Number two, the second source of losses is losses due to currents flowing in the waveguide walls. Losses due to currents flowing in the waveguide walls. So another thing we need to know is that these losses can also be due to other dielectric fillings. So losses due to dielectric fillings. Inside the waveguide. So finally, we're going to talk about the advantages of waveguides. Number one is less expensive to manufacture because they are oral. Less expensive to manufacture because they are hollow and so consumes less material. Number two is that high power handling capabilities. High power handling capabilities due to the high frequency of operation. Number three, we are talking about lower power losses. Lower power losses compared to coaxial transmission lines, compared to coaxial cables. Because of the skin effect principle. So lastly is I can give you is the high operating frequencies.